at Livermore, right in the early phases of the radiation, when we first started doing radiation-driven implosions. Involved in, as time went on, I had various levels of responsibility, running the ICF program, then eventually AD. So I was very much involved in, as we expanded the ICF facilities and program to the weapons program, the science activities. HEDP started a lot with the stuff that I and others were involved in. I don't take credit for it. I was involved in it. And obviously in the early phases of stockpile stewardship, and then selling and articulating the need for NIF and the role that these facilities would play in the national security arena. So I feel something like Forrest Gump at some point, being at different places, at somehow finding myself at interesting times. So this talk is motivated by all of us expect or hope, and I'm sure we will have other facilities beyond the present suite of ICF facilities, NIF and the like, as we move forward. And it's important to understand the complexity of getting these facilities and these programs. It's not just doing good science, it's politics and everything else that you can imagine, community building. And so what I thought I'd do is just show my journey, if you will, through that whole process. And hopefully it will be helpful for those in the future who are trying to bring new facilities, new capabilities to the country. So next view graph. All right, so here's the really outline. So as I said, I started in the program. I joined Livermore in the Ides of March in 1977, just in the beginnings of the radiation-driven program. I remember when the Shiva building was just starting to be built, so it was interesting times. My first work was at the Argus laser, which I'll talk a lot about, and some of the lessons we learned in doing that. Then there's some example of some other programs of scale. What have we learned from them? And then a lot about NIF, of course, the background, that is both a technical approach and a political approach, and there was all of that involved. It was very interesting times. And then a little bit end with lessons for future large-scale facilities. Now it's important, to look forward. Of course, we always must plan for the future. But there's this great phrase in Lord of the Rings, which my son got me to watch. This phrase that was once history becomes legend, what was once legend becomes myth, and what should not be forgotten is forgotten. So my hope is that this type of talk will help people remember, and actually will keep me remembering what would happen then. All right, next view graph. So this is ANOVA. So again, any inaccuracies, of course, or remembrances that are maybe not jive with someone else or mine. This is how, as I remember it, and it's as accurate as my memory serves me. But this is a great picture of NOVA laser. NOVA was really the first, I think, highly successful facility that we built, and we'll talk a lot about that as we go through the talk, and the role that it played in securing NIF and actually establishing ICF facilities as part of the stockpile stewardship program. Next. All right, so going back into the 70s, it was a decade where actually building lasers all the time. Started off with Janus, which was a two-beam laser, and actually it's the Jupiter laser now, so it hasn't gone away. But that was that was the first solid-state laser that at least I'm aware of. Livermore had a CO2 laser. You can imagine we even had an argon fluoride program. These things are long forgotten. My work really started as a staff scientist on Argus. Argus was a two-beam, 2 kilojoule laser, and it really employed the first really modern architecture and these solid-state lasers that have been continued throughout ever since. Shiva was the first really big laser. It was a 20-beam, 10 kilojoule laser. And it was really a place where we're going to do a lot of the radiation-driven implosion experiments with the goal of demonstrating you could ablatively implode something to high density. Then, of course, there was NOVA. NOVA was designed for ignition and gain. I have the famous plaque that I gave to John Emmett at the 40th anniversary of the laser program several years ago, and it had a plot of performance as a function of time.
Conventional operations under limited nuclear conditions.
Something else.
Integrated operations. Called on to do so. Planning is essential.
Someone is talking, not me. Or am I back? Can everyone hear me?
Yeah, you're back.
Yep.
Yeah, you're fine, Mike.
Okay.
Yep.
And then Nova, which was going to be a 20-beam, 240 kilojoule laser for ignition and gain. That was the plan, and that was, they're all basically either being designed, being built, and planned over the first, over the 1970s, early 80s. And of course, all of them used neodymium glass with 1 micron radiation, and laser beams were unconditioned. There was no attempt to do any spatial or temporal modulation or adjustments to the laser. So they're, I like to call, unsmooth laser beams. That was the program. Next. So of course, why was X-ray driven approach of IC at Livermore the way we switched to? If you look at John Knuckles' paper, of course, there's classification issues, but was direct drive. And of course, NIF has done wonderful work on radiation-driven implosion. But what were the motivations at some fashion, even going way back then? And of course, NIF has done. We'll get to that a little bit later on. So of course, let's talk about direct drive at the time. Remember, this is a viewpoint from the 1970s. All right, next view graph, Gene. So again, the 70s direct drive had lots of challenges, and one I'd like to always illustrate. You look at the middle picture. That's what a laser beam like. Remember, we shot these lasers. These lasers were focused at targets in the intermediate field, where all the phase and modulation, amplitude modulations were enormous, and you had enormous structure in the laser beam. And of course, where the laser is hot, it ablates more. Where it's less hot, it ablates less. And so this is imprinting on steroids. And of course, at that time, hydrodynamic instabilities, of course, were seeded by this the imprint, which was obviously extreme. And electron-driven ablation is less effective in, let's say, is more susceptible to these instabilities than X-ray-driven ablation was. And of course, the laser beam interacts with the target, and so if there's any LPI issues, it's close by to the target. That wasn't as thought the most at that time. It was really the quality of the laser beam, and that electrons were flux limited, that they didn't transport and smooth out the energy in ways we thought. This is back in the 70s, of course. And of course, it's a little bit lower exhaust velocity, but that wasn't the driver thing on this. But you can see there's a picture on the far right which shows the shell breaking up from direct drive. So X-ray drive became the dominant thing that we looked at the time, and that's continued to this day. Next. But what else? There are other motivations for this, of course, and we've seen how challenging this is. But the idea was, well, we had a semi-control by target design. We could actually fool around with the whole rooms and get the symmetry necessary to get these high convergence implosions. We all know how challenging that is, today. But back then, it was thought that this was something we could do in a more straightforward manner. Didn't require high quality laser beams, right? Because we didn't worry about these imprint. The whole room would smooth them out. But one of the things that was learned on, I think, early on is that beam quality impacts instabilities. And I remember when we were finally taking pictures of backscattered light and such, we would see that the brilliant light was just where the beams were hot. So that was, but it was not considered, it was considered an advantage. Of course, hydrodynamic stability, I already mentioned that, good rocket efficiency. And also the lab was familiar with X-rays, of course, because of the nuclear weapons program. And importantly, energy was still always a major consideration of how we did these things. If you look at one of the original statements in Congress when ICF became a separate line item, it said two things. It said that this would help the nuclear weapons program, particularly in the absence of testing. This was done in the late 70s, a statement, and then long-term for energy. And at that time, we thought lasers are pretty inefficient. This was before the diode lasers came along. And so if we ever wanted to have efficient driver efficiency, so we wouldn't have to have enormous gains, heavy ions look like a good way of doing it. And so if we made whole rooms, we made X-rays with lasers, we made and showed how a capsule responded to X-rays. Well, if we made X-rays with ions, we'd already have the capsule physics done. And so it was a transferable view towards that. And of course, the other thing was that we did not require 4 pi illumination. So when you were looking at chambers for energy, you could imagine getting away from the first wall problems with the high neutron fluence from DT fusion by making essentially wet walls. The fly was a material, was fluorine, beryllium, lots of different things. We would both interact, it would stop the neutrons, breed tritium, and prevent structural damage. So there were these longer term considerations were involved in it too. So a lot of those things are less because we've focused so much on the weapons applications, but that was a motivation for the program for a long time. Next. So the first real major campaign was going to be on the Shiva laser. And the goal there was to compress DT to 100x, 20 grams per cc. And the campaign was going to be done on the Shiva laser. It was a milestone of Shiva, and again, the radiation-driven implosions to 100x. We're going to use 1 micron light, about a few 100-volt electron radiation drive. The target was not cryogenic; it was high-pressure DT with a silicon pusher and the CH ablator. And when I look at the diagnostics, we play in the program now on NIF and Z and Omega and elsewhere. It's just remarkable, but where we were back then reminds me of the Wright brothers. You'll see that a little bit later. So they had many diagnostics, and the principal one we used for density was actually measuring the pusher ROR, the glass pusher ROR, and I was involved in that. And we used a neutron activation technique. The silicon would be activated by a neutron. You'd make aluminum-28 and measure that radioactivity, collect the mass fraction, and you'd be able to get the figure of the ROR. We also had a time of flight detectors, and of course, ROR was too small to use them, except they measured the yield. And if you look out behind the old Argus building, you'll see the neutron time of flight little cabin there that the detectors were. But before you do it on Shiva, well, let's try it out. Let's start doing some experiments on Argus. And so we used the Argus laser, and I was involved in that. We had 2 kilojoules, again, unconditioned beams. And again, diagnostics were limited. We have a Dante, which you all know well. And over on the right is the first cartoon. You'll see that's Harry Kornblum. Harry was on assignment from L Division. Harry was the father of Dante, and a great guy, and I'm sure he's long retired. He's holding a stick that has Dennis Matthews' head on it, by the way. So we had a Dante, only 5 channels. We had a crystal spectrometer. It was called a Henway. It was time and area to look at the M-band radiation from gold and neutron flight. So not a whole lot of diagnostics. And if anyone ever wants to know why these spectrometers were called Henways, there was the engineer or physicist did it was a guy named Lou Capel, and the engineers asked him, well, how much does this spectrometer weigh? And he says it weighs as much as a hen, so it became the Henway spectrometer. All right, next. So of course, what was this? And this infrared catastrophe was laser plasma reaction physics in the long scale length plasmas that were now in whole rooms. I won't go through all this litany of instabilities. They're all well known now. But at that time, we were just beginning to explore these things and obviously see their presence. And there's a threshold underneath there, but by Marshall Rosenbluth and Lou. Marshall was a wonderful partner in all this, a wonderful friend and scientist. And there's Bill Crewer telling, I told you this was going to happen. And he's wearing a T-shirt, which you probably can't see, and it's he survived the Livermore earthquake, because we had a great earthquake. I can't remember, in 1979 or whatever. And Bill was giving a talk, and Carol Alonza asked him, well, if the dimensions of the plasma are the dimensions divided by the wavelength, so that makes the wavelength, that makes the plasma small. So isn't CO2 a good laser? Bill was ready to answer, then the earthquake happened, and when I looked up, he was the first one escaping the building. So I drew a cartoon of him with his earthquake shirt. Of course, the other one there was Nat Fitch. I drew that for Nat on his 65th birthday, and Nat is a wonderful plasma physicist too. He wasn't involved at that time, but Bill, of course, was, and Bill had a wonderful group who was involved in telling us all the things that could go wrong, which of course did. Next. All right, so it's very simple in hindsight. Why did this happen? At the time we were doing direct illumination was relatively small capsules, only a few hundred microns in size. Intensities were less than 10 to the 15th. And if you look at what the Raman scattering threshold was for a single beam in the inhomogeneous plasmas, it was we were below threshold, so you didn't see things. So we're more concerned about resonance absorption and things happening near critical. But of course, when you shot these beams into a whole room, millimeter-sized whole room, you had long plasmas, and thresholds were well exceeded. And I used to say every photon looks like it Raman or Brilon scattered in these plasmas. So of course, that was a major, I'll say, unhappy discovery from the program back then. All right, next. So what do you do? So run at lower intensity, but we all know what that does. It puts the stress on the hydrodynamics. You want radiation temperature. You want the ablation pressures, both in indirect and direct drive, to be high enough so you don't have to have IFARs of unsensible values. So what you do? Make the wavelength short. Well, that was a tough game right then because we know the thresholds instabilities. All I lambda squared is a parameter, so shorter wavelength means higher intensity is possible. but a lot of issues with optics and actually how do you convert large aperture beams. So that was something that was a major problem at the time. You also can destroy the laser coherence. These are coherent processes, and so this motivated, of course, a lot of things that were done at Rochester, NRL, and Osaka, basically to do phase plates so that you could at least take the structure in the beam and put it in a more controlled fashion, knew what it was, and then put a little bit of, and then after that, a little bit of temporal smoothing, limited by the bandwidth of the laser. So you would actually take these high frequency speckles, that's what a phase plate does, and move them around on time scales so that filamentation would happen, and hopefully you could reduce imprint. Of course, then you could do high bandwidth, but anyone who knows lasers knows that lifetime to upper state and bandwidth are related. And this is a laser that stores a lot of energy for a long time, doesn't have much bandwidth. The bandwidth of these laser time would limit you to basically less than a terahertz, and you need more than that. Now, of course, there's been other innovative things that Bedros has come up with, a thing called stud pulse. He's always good to come up with names where you basically move the intensity around in both time and space on time scales fast enough not to drive instabilities. I hope both of these things will be future exploration for what we do in these facilities. But all lasers today operate at short wavelength and employ some level of beam smoothing. Now, the other thing that this actually won a Dawson Award back in 1993. I personally thought this was such an advance of the field that we needed to have it recognized by the plasma physics community. So I submitted this as for an award for the three places. It took a little bit of convincing the committee that this was plasma physics and not just technology, because the impact of plasma physics, but they won the Dawson Award, which was great. Next. All right, but what were the implications of this work? First of all, it was clear Shiva was going to have lots of problems. We're going to have it was going to be a big issue to get this milestone. And Shiva was already under construction, right? And Nova was in design. There was some hope that maybe the plant that we had more energy would get better, but we know that's not the case. And then converting Shiva to the green was discussed, but it was not pursued because, first of all, Shiva was underway. There was no time to do that. Nova planning was also underway, and there was no infrastructure in the community to get large nonlinear crystals. There were people had done KDP, but they had done it at small scale, and so do it on a large scale that we had for our multi 10 centimeter aperture beams wasn't there. So Shiva went along with that, and then Argus switched to doing laser plasma reaction physics. So we then took the KDP that we were able to get and limited us to basically 100 joule experiments. So I was involved in that. I was with Bob Turner, myself, and Don Fillion, and other people were involved in that. And so we did experiments at 1/2 and 1/3 micron, again, with unconditioned beams, and was limited by the crystal size, disk and whole room targets. And now we started putting all the scattered light diagnostics, high energy X-ray detectors, so we can actually measure the hot electrons or their X-rays that they emit. And we put a lot of detectors to look at Raman, Brolon, and 2 omega PE. And this was challenging with 1 micron, as you imagine, because Raman, the scattered light from Raman is in the near infrared, where detectors at that time were pretty limited. So going to the green and blue made the study of Raman much easier to do. Next. All right, but what happened? In the meantime, back in DC, well, Nova was canceled. Because the problems we were having with getting the milestone from Shiva, the large number of hot electrons, so Nova was canceled, and it took time to try and get this diagnostic that would show that we actually did get high compression even with these low yields. So we had to design. So I did those experiments. We had to design a pretty sophisticated nuclear detection system because we didn't have many neutrons, and again, these ρR measurements required neutrons. We had a fast rabbit system there, so I sure wish one of these days we get rabbit systems in our machines today, but we actually had a rabbit system on Shiva and then, of course, on Nova. Had to figure out how to collect the pusher, and we actually made shape charge whole rooms. I won't go into the details here, but all this stuff was classified, and it was very frustrating for many of us not to be able to talk about this. And we got a very sophisticated X-ray detector because when the aluminum-28 decayed, it emitted both a beta ray and a gamma ray, and we made a coincidence detector which had low background and high sensitivity. But it was clear then Nova was not going to be able to get fusion ignition and gain. What do you do? Well, if this had happened, where would we be today? I don't know. Would have been the end of the program, but it sure was going to be a major problem. Next view graph. But that didn't happen. So what, and I'll tell about that. So what was the lessons learned from the 100X campaign? First of all, we were doing experiments in regimes that we had very little experience with codes that had been untested or very not nearly sophisticated, and overconfidence in modeling simulations. This is a theme that this program, the ICF program, has had in its history. Insufficient peer review was classified, so you couldn't really have the broad community get involved in this. I remember getting papers from Japan and Germany on whole rooms that we couldn't review or talk about. So insufficient peer review. And then this is something which is a theme for me as an experimentalist, at least in my earlier career, is you need leadership that has all the spectrums of expertise. And here, John Emmett, who deserves enormous credit for establishing the ICF, the laser program at Livermore, and John Knuckles, they were the drivers for the program. Experimentalists were basically make the measurement for us. And that's not good enough, because when you have a program that doesn't have this experimental leadership, which is a partner here, so the intellectual, if you will, contributions, not just making diagnostics, but actually putting design in the program, just wasn't there. And so lessons learned, you always got to have that. You'll see that later on. Of course, what does that lead to? Inadequate diagnostics. And then also you had to establish trust with DOE. So, all right. And there again, there's another cartoon. That's a young John Knuckles. And you know, John deserves enormous credit. He's the father of the field. You know, one of the most innovative people I've ever met. A wonderful guy, a great friend, and he was, of course, lab director at a critical time for establishing stewardship. All right, next. All right, but what happened? So we obviously NOVA got built. So we had some nice results. So Argus, even at the 100 joule level, showed that short wavelength makes a difference. I remember 1979 APS meeting in Boston with Edward Fabre, showed work from a cold pot technique with a 4th omega laser at 1 joule, showing things looked a lot better. And of course, the RadChem demonstrated we got pusher RORs that we could infer that reasonably high densities. But of course, the yields were too low, but they weren't a milestone. And I remember in Boston being very frustrated not being able to talk about what we were doing for our short wavelength experiments because we're all classified. So it's sort of frustrating, but nonetheless, it helped. But so what we took that information, then what happened? Next. So NOVA was changed. So NOVA went from a 240 kilojoule, 20 beam, 1 micron laser to a 30 to 40 kilojoule UV laser. And the big issue was it was going to cost the same, about $176 million. So NOVA changed and became much more a physics facility. And of course, the philosophy of the program strategy came, well, we're not going to get ignition with NOVA. We have to plan for the future. And that, remember, it's important to realize how big a leap NOVA was. We had 30 kilojoule UV at Argus, and now we're doing 30 kilojoules on NOVA. So it was a major technological advance and scientific advance to be able to do that laser. And the mission now, of course, was now, we got to make the case for a future facility that's going to be much larger than NOVA was planned to be. Data tells you what works and doesn't, and so it was clear data was telling us we needed a much bigger facility. And so started looking at things like what's called Zeus, LMF, a multi-megajoule facility. And it's important here that at that point, weapons science was not much a mission. We weren't focused on supporting the weapons program as part of what NOVA was doing. Nuclear testing was still ongoing, and the weapons program's focus was on testing. So we had very little interactions with the weapons program at the time. Now, one of the things that was done was to build the novette laser. So novette laser was funded as a bridge between Shiva and NOVA. It had several purposes. One, to demonstrate the NOVA technology. Secondly, is to conduct experiments now with multi-kilojoule levels at half micron and in the deep blue, the UV, at 4 mega. And then it was we operated that while NOVA was under construction, so people were still doing research. And it was the first 2 beams of NOVA. And so the whole idea is when NOVA had 8 beams installed, we'd bring the other 2 beams over, and then we'd have a complete NOVA. So Novette was an interesting facility, and we'll talk about that next. So there are good lessons and bad lessons learned from Novette. So what are the positive lessons? First of all, short wavelength continues to be positive at multi-kilojoule energies. Now, beams were still unconditioned, but we had good coupling at the scale, and we didn't see the infrared catastrophe. We didn't have a visible or ultraviolet catastrophe. And it really, was the first weapons research. This was the beginning of the time of Star Wars. And so the weapons program, or that part doing Star Wars, was interested in doing some laboratory work. And so we actually worked and made the first laboratory X-ray laser. That in Princeton did the same thing, but a different scheme. Yeah, Morty was a critical player in that. Dennis Matthews, Peter Hegelstein, and the like. And this was a great achievement for the laboratory. Bill Krupke has some interesting stories about going to the Soviet Union not too soon thereafter and telling about this and the impact it had on some of the Soviet scientists he talked to. And importantly, it was the first Dawson Award the ICF program ever won in 1990. So very good stuff. You see the X-ray laser there. We had cylindrical line focuses, and so we were able to do some very interesting stuff. And from a laser physics standpoint, actually we were able to show we grew large KDP crystals, 20 centimeters, and importantly began to demonstrate the supply chain that you would need to build the Nova laser. So they're all the good things, but there were some bad things. Next. So first of all, here's the X-ray laser team. And you can see there's some interesting players there. There's Alan Wan is there. You see Brian, there's a lot of people. Andy Haase, there's Brian McGowan, Bill Krupke, and of course you see Bill Goldstein right there. There's Morty, Dennis Matthews right up front. There's Peter Amet. We had a lot of interesting people there. Unfortunately, it looks like a picture from 1955. It's just a bunch of white guys. And so diversity is, I'm sure, glad to see how much diversity and inclusion we're doing now, but we have a long ways to go. But it's great to see the people were involved in this at the time. And it was this was a 30-year anniversary held in Livermore a few years ago. Next. But what were the bad side? So what happened was the laser diagnostics being developed at the time were not very adequate. The original laser diagnostic package put in novette, which had a beam splitter which directed the light to a diagnostics platform, was the coding was dependent on humidity. So we would have the laser, would have all the pulse power set the same way, the oscillator set the same way, and we see that our measured energy would be vary by factors of 2. What the hell happened? Well, it turned out that that was flawed, so we had to replace the diagnostics. At that time, the laser people were now working on NOVA, so the diagnostics were put in by the experiments group. And what did we want to have? We wanted to have the total energy, we wanted to have the time history, and we wanted to have an equivalent plane to show us what the beam looked like in the target plane. But we didn't care about the near field. And the near field showed that the laser glass was filled with platinum and would severely limit the energy that NOVA could do. I'll never forget, I was in my office and one of the techs came up to me and said, you got to see what the laser looks like because we're just dismantling the amplifiers to take them over to NOVA. And the laser glass looked like someone had a shotgun and shined it on the laser. And of course, that didn't impact the measurements we made because we're looking at all that high spatial frequency stuff we didn't detect in the spatial imaging, so we didn't know it. Major issue. And also, and all the other lessons learned was that the experiments program was focused on novette and not on NOVA. And so when NOVA came up, NOVA did not work very well. Some of you have probably heard the term precision NOVA. I'll talk more about that. But precision NOVA had some goals in this, and it was basically, we got to fix the laser because a 1 micron performance is 120 kilojoules, half of the original 240. We had to figure out how to get frequency conversion because the frequency conversion for 3 omega did not work either. Turned out it was very sensitive to polarization. So we had a bad 1 micron laser and a bad frequency conversion. And there was no discussion of power and energy balance. And so we had to start up a program to be able to measure those things in a way that was accurate to the necessary. And Bob Coffin will remember half the time we'd shoot a hole room, we would hit the entrance aperture and not go through the hole. So we had to learn to point it. Now, one of the things that came from this, and you'll see it in I actually forgot in the X-ray laser thing, a lot of spin-off diagnostics and technologies came from this. So some of you may have heard about microimpulse radar. That came out of our program to measure power balance on NOVA. And that's had a lot of technology applications. It's called ultra-wideband and other contexts. And the X-ray laser, which I had forgotten to mention, that inspired what is now called EUV lithography. Andrew Havrilik was an engineer that with Nat Siglio, using the X-ray mirrors that we designed for diagnostics and the ability to make X-rays with the laser. And so that is now the principal way that people are making microchips. They're doing that at 7 nanometer scale, and they're working now to get 5 and 3 nanometer scale. And it's an ICF derived technology. Most people don't either remember that, know about it, and it doesn't get talked enough. And of course, don't forget diagnostics. So this is one of my more famous cartoons. And you know who that is? That's our good friend Joe holding a Walter microscope. Next. All right, what are there other programs that had some features about the 100X? Nick clearly had some of those features, but let me talk about Star Wars for a minute, because that was an interesting thing to see how that went too, because it was happening around the same time. All right, you all know Star Wars, and this was a way of using innovative science and technology to make a nuclear explosive not release its energy into forward pipe, but into directed contacts. And X-ray lasers was a major thrust of that. Hank Shea, who came from the ICF program, ran that program for a while, and this is a cartoon of him. Hank was a great guy and did a lot of very important in Halide Centaurian and other things. Someone who should not be forgotten for his contributions. Next. And of course, there's Edward Teller. That's him as the Ever-Ready Bunny. I drew that for him for his 90th birthday. But what did the X-ray laser program have that shared with the 100X? First, relying on numerical simulations and untested physics regimes to do this level of spectroscopy and kinetics was something was not necessary in the weapons program. The leadership, again, experimentalists played a minor role in the beginning, but that changed after some challenges happened in the same way that 100X changed. Inadequate diagnostics, of course, always results from not sufficient experimental role. And but it's important to note that Dick Fortner, Rick Stewart, Mark Eckert made major contributions. A lot of the gating technology came out of work that Rick did. Rick is a forgotten hero, sometimes forgotten hero for a lot of the diagnostic innovations that he brought into the program that we still use today. Next. All right, so bottom line, you need theory, modeling theory, and experimental expertise are essential components of a program. So here's, on the left-hand side is Livermore's first nuclear test, Ruth. And you see that the only thing that went off was a high explosive. There's a famous telegram, I think, that Los Alamos sent to Livermore saying, now that you're done with the tower, can we use it for our experiment? And of course, there's a picture of NIF, emphasizing, again, you need all of those elements for a program to be successful. Next. Now let's talk about NIF. All right, next view graph. All right, so there's a nice picture. And all right, so another cartoon of a Family Guy. Next. I have to advertise my cartoons. All right, so let's go back to the 80s and 90s about Journey to NIF. So of course, after the reality of data made it clear that we needed a facility of scale to get ignition in the laboratory. So we started working on things about the megajoule scale and a 1/3 micron. And again, with unrealistic costs, but again, when you're starting things out, cost is something you don't think about in the beginning. And so the cost was going to be hundreds of millions of dollars. And we all know that's billions of dollars. But at that time, we started looking at that. Target game was going to be 100 volt, 100, with radiation drives of a few hundred volts. And NOVA developed into a physics and user facility. The platinum glass problem was fixed. Jack Campbell was a hero of that, working with both Schott and Hoya. We got the full 1 micron performance. I remember it's my only time I've ever been in a hot air balloon, probably never happen again today. After we got our milestone of full energy, we had a hot air balloon at the site at Livermore, and we're giving rides up and people in the balloon with 100 kilojoules draped on the side of the hot air balloon. We fixed the frequency conversion. John Murray and John Hunt and others determined that the small depolarization that happened in the NOVA chain was enough to make the type 1, type 2 not work. And so it's type 2, which is which NIF has too. And importantly, we built a second target chamber. We want to develop this into a user facility, and we took the novette target chamber. I remember when Dennis Matthews and I went to John Emmett to say we want to add a second target chamber to NOVA, said that's the stupidest idea I ever heard. And we said, well, this is how the laser sits there while people are thinking out what to do in the next experiment. Having 2 target chambers was a very important part of making NOVA a very useful facility. And of course, there also was great progress in direct drive. This beam smoothing that Rochester and NRL developed was implemented on facilities. and had a big impact on the viability of direct drive. And Nova was the last laser to adopt it. We put 1D SSD on Nova, which was very important for us making gas hull rooms work. So this was great progress at the time. And of course, NRO went to KRF. They dropped their 1 micron program, and Rochester, of course, did the triple glass to the mega, and everything's done that. Los Alamos said, all right, enough with CO2. Now let's go to KRF, and they started a program called Aurora. And it was designed as a KRF facility roughly at the Nova scale. So they started that program then. Next view graph. Of course, working with DOE was an important part. There's a cartoon of Marshall Slater, who was running the ICF program for a long time, and he used to complain that he saw me more than his wife. But developing a partnership with the agency was always a critical part of this. Next. So if you ever go down to P24 at Los Alamos, you will see one of the old CO2 amplifiers. That's me standing next to it. I always said, is this a basic place where visiting scientists at P24 can live? Or is this a CO2 amplifier? It's a CO2 amplifier. You see the size of these things, but that is now just a historical artifact and a nice monument out front of P24 in Los Alamos. All right, now, and of course, Halide Centaurian happened in the 80s, and Halide Centaurian was, we can't talk about that, but many of you know the role that it played in the program. It was conducted by Los Alamos and Livermore. It's classified, a lot of really nice work there. Steve Hahn, Max Tabak, John Lindell made major contributions. Hal Alstrom, we started having a migration experiments program over into that program. There's Hal Alstrom on his way to Nevada. Eric Storm made a big role. So this was a major success. I was there for one of the key experiments. It was interesting to be there at a nuclear test. And I remember when I saw the results, I thought this is going to have an impact. And as a result of that, Congress, inspired by the lab, demanded a National Academy of Science review of the program. And this is a famous Coonan review that was done in 89 and 90. Next. So this was pivotal. There's no question about it. There's, again, Marshall. So we proposed, Livermore proposed the LMF as a next step. Again, it was a 10 megajoule laser, target gains of 100 gigajoule yields. And the NIF said, you're out, this is too ambitious. Talking to Kuhn, you're out of your mind. You have a 30 kilojoule laser and you are making maybe 100 joules of neutrons. This is too big a step. So they said no. So all of a sudden that changed our strategy. And of course, they also had a preliminary report saying that Livermore and Los Alamos are still in competition. Let's see what the next facility should be. Should it be a KRF facility or a glass laser like Nova? And they did a preliminary report, and I remember getting it. Joe Kilkenny, a guy, said, this is crazy. Nova's operating, but Aurora was not even built. And yet we're going to be in comparison, we're going to have that in competition. It would put the program next facilities in the indefinite, and I mean indefinite future. There's, again, a nice picture of Marshall. Marshall, one of the heroes of the program in many, 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 many ways, and instrumental in getting the general community to believe that ICF had validity. Next. All right, now it's all about the technical approach. All right, so this encounter with the NAS, because I was there running the ICF program then, and so it really began to alter our strategy. So now we've shifted to what's called the Nova upgrade. Let's keep the Nova building intact and let's put a megajoule laser inside there. But we couldn't put 10 megajoules in there, so could we make a credible case for an igniting plasma at megajoule scale? And what we needed then was peak radiation temperature of about 300 volts. And we demonstrated that on Nova. We were given the 1 micron catastrophe. We were afraid of pushing the whole rooms to higher temperatures, but we successfully did that on Nova, again, at the scale of Nova. And that was a big, important milestone of having a discussion of megajoule scale facilities. And then again, now, of course, then we're not going to get gains of 100. So ignition and modest gain became a focus. The other thing learned from that is there has to be better ways of informing committees and stakeholders, because when the National Academy of Science met, they had to be re-educated. They didn't have a history to really look at and a program that they were familiar with, or a committee that reviewed the program from the outside. So they recommended we had a standing committee called ICFAC. People like Marshall Rosenberg, Arthur Kerman, very well-known people in the community and outside the community, monitor the technical program. We put together a technical plan. It was called I made it called a technical contract that would basically guide the research on Nova. And would be endorsed except by the whole community, including people like Steve Bodner. And it established milestones that this committee could follow. And also, we needed to improve NOVA. It gave us good excuse to improve NOVA and the whole Precision NOVA program. And again, at this time, direct drive was too immature. Omega, the Omega 60 had not been built yet. Pulse power was still on light ion beams. They had not yet gone to the Z-pinch and the like. So there really was no competition for HEDP and ignition unless you put these lasers. And then, of course, NOVA evolved as a user facility, and with increased emphasis on getting the weapons program to participate. And people like Dick Lee and Alan Spiro were very important in making that happen. And AWE was one of the first weapons users in that. Joe Kilkenny was very much also involved in that. We also started a science program because it became apparent that if we wanted an endorsement for such a facility that would follow NOVA, we had to have more people thinking this was useful science, not just supporting, not just doing ICF and beginnings of weapons. So we started what is now everyone calls HED physics. So I remember Bruce Remington came to my office and we had a conference that he had on lab astrophysics. And I remember I have a fax I sent to Vic Reese that basically said we just had this conference and there were people from outside the traditional community that Bruce held in Pleasanton, and we should start this new field. We should call it high energy density laboratory physics. I still have the fax that I sent to Vic saying that. And then with all that done, the final NIS report endorsed the Livermore strategy and recognized NOVA as a premier facility. Next, a lot of work. So technical contract, I won't go through a whole lot of details on this, but we had 12 physics milestones. John Lindell and I and others put this together that basically showed what we could do on NOVA that would reduce the risk as much as possible for NIF. We didn't do any cryogenic experiments because we only had 10 beams, 5 on the side. We didn't think we could make a credible implosion with that. And we had everyone participate. This was endorsed by the community, this ICFAC committee and DOE. And it's important to know that it didn't eliminate the risk, of course, but it addressed all the physics that we thought we could do on NOVA. And so it let the groundwork. This had to be approved by ICFAC before NIF would move forward. Next. So this was a great time for the program, I think, overall. Precision NOVA was successful. We did all the things about its power, its energy, the diagnostics. Many became an effective user facility with almost 13, 14, 1,500 experiments a year. A lot not done by the weapons program now. Los Alamos and Sandia played major roles in this. They were given some of the key elements for this technical contract that they were responsible for. Extensive diagnostic development. That was the first time the use of framing cameras, neutron spectroscopy, all the stuff we do today had many of their origins back in NOVA. We started the lab astrophysics, the first equation of state that was done there that actually had to be worked on with Sandia too and fixed. We demonstrated the first petawatt. So the 80s, mid 80s to mid 90s were great years for the program. Lots of awards, the 3 Dawson Awards, I mentioned one of them. Excellence in plasma physics, popular science, so we're getting a lot of visibility. If you look at the R&D 100 awards, which DOE makes a big deal about, if you look at that as a function of time, you will see a step function increase around that time from basically the laser program and Livermore and then the rest of the program. And DOE became they became an advocate. And you see there, one of our greatest advocates was our good friend Dave Crandall. He became head of the program after Marshall, and he has religious fervor still to this program. Next. And of course, we did the petawatt, and I think that was a major inspiration for a lot of the high field physics that we do today. It won, of course, a Nobel Prize for the inventors of the technology, Donna and Gerard. And you see in the lower left, you see myself there with Donna, and the first petawatt done at Livermore. And there's Mike Perry standing next to Charlie Towns. Mike was a key player in developing that petawatt at NOVA. It was a great success. And just an aside, I won't say much about this, but Livermore is involved in directed energy programs. How to use high power lasers for national security. There's 4 approaches, and 3 of these approaches either were invented by ICF people or relied on ICF technology. So one of the things that I think we have to do better as a community is to continue to inform the stakeholders and our sponsors about the role that the technology development of the ICF program does in national security. Next. And also did a contract for the beamlet. I know we're looking at what the cost of any new facility would be, but to give you a sense, if you had just taken NOVA and scaled it to NIF, it would be tens of billions of dollars. And NIF, we had to show that we had a technology and approach that would make the cost be much less than that, because no one's going to buy a $22 billion or tens of billion dollar facility at the time. Next. So to do NIF, you needed miracles, and you had to get the supply chain. Laser glass manufacturing had to be radically changed. Schott and Hoya did this, and Jack Campbell again was the hero. We had to develop a whole new architecture, multi-pass architecture, and people like John Chenholm, John Hunt, and others developed that. Howard Powell. We had to develop a large way of ejecting the light from a cavity, an unstable resonator, effectively, and that was Mark Rhodes. That was one of the great miracles of NIF. Had to have spatial filters stay open for tens of nanoseconds, a big deal. And of course, flexible and pulse shaping. NOVA was the first one I mentioned, did pulse shaping. We did it by cutting transmission lines and sending a voltage pulse down there would vary in time onto a Pockle cell. Well, Russ Wilcox came up, I remember, to me and said, look what the telecom industry is doing. We can make programmable pulse shaping. So Russ is a hero for that. All this was demonstrated on beamlet. Large KDB crystals adopted from Russian research, Natalia Zatseva. We hired her, and that was, you can imagine, a little challenging to hire Russians into the lab. Harry Roby, of course, and beam conditioning. So beamlet demonstrated the architecture and many advanced technologies for NIF in the 1 micron component. Next. And it was a major advance. It's now at Sandia, doing a lot of great work in supporting the Z program. And when Livermore did the 10-year anniversary of NIF, I thought the video was very well done, but all the assembly and the stuff that Ed and the team did, which were great stuff. But there was not enough airplay, I think, on developing the supply chain and the technology that had to be developed that allowed the laser to happen too. So I hope version 2 of that has a little bit of that added to the already great stuff it has. Next. All right, so about politics. Can't get out of that. All right, so what happened to NOVA upgrade? Well, after we got the National Academy report, we proposed it. And there was a briefing at DOE with Will Happer and the like, and our cost was it's going to be about $350 million. It was going to use the NOVA building, and CD0 was rejected. You all know what the CD0 is. That's critical decision 0 to give the mission need for a program. It was rejected without prejudice, inconsistent with the value to DOE and the nation. Remember, nuclear test was still ongoing. So what's lesson learned? These reports that endorse you are not enough. You need much broader support to be able to move forward, and actually some interesting times. So next, 92 and 93 were pivotal years for the whole ICF program. We stopped testing. We had it gave an opportunity to get a CD0 for now was we called it NIF. DOE named it IDINT. The CD0 mission need, we're trying now to get this in before Admiral Watkins, who's the DOE secretary, stepped down because we had a new administration coming in and we had to start the whole process over again. So it was the last action he did as secretary to sign the CD0. Will Happer was instrumental in making this happen. We emphasized nuclear weapons effects testing. I remember Watkins telling Will and myself, well, the bombs aren't going to change, but electronics in them are, so we got to have a way of testing that. And ICFAC recommended going forward, and the weapons program was now heavy users of the program. Now we had a new administration, but also presented a challenge with, I'll go in the next view graph. Next. And the testing was a real traumatic thing for the laboratories. And, and in my opinion, we were really pretty much unprepared for that. It was a political decision, not a technical one, because the Soviet Union was in a process of collapsing. Cold War is over. What do? So we had the great error. Let's take all of our science and technology and help American industry. That's actually where EUV had a lot of airplay back then, as you can imagine. So Vic Reese, who is now the Assistant Secretary for Defense Programs and is the hero of stewardship, had a whole series of workshops of what do we do? And they had a key one at Sandia, and we proposed NIF, or what is now NIF. Arthur Kerman, not Livermore, gave the talk about this was an important thing and critical for the community. and Vic brought into it. And Bob McCrory was very helpful in doing that too, because we obviously needed the community support. Next. So stewardship then came from this. It was, as you all know, stewardship 1.0. Now we're doing stewardship 2.0. There's a cartoon of Vic. And you see he's wearing a NIF is my life t-shirt, and he's holding a micro impulse radar, by the way. Vic is, of course, the champion of also high performance computing, the ASCII program. You know, Vic used to he would always give good talks, and he would say that experimental facilities like NIF and ASCII are like, if you know 1930s and 40s Hollywood movies, it's Fred Astaire and Ginger Rogers. Fred Astaire gave her class, and she gave him sex appeal. You needed them both. And of course, 1994, the Defense Authorization Act established SSP. And Vic, with a lot of people, a lot of work, Siegfried Hecker, others really were in the lab itself, Livermore, got Russia, China, and France, UK to eventually agree with the cessation of testing. Big deal for the program. Next. But I want people to understand this was really hard, to get NIF. First, the end of the Cold War. Why would you spend money on nuclear weapons? You're done. You won. You know, democracies generally demobilize after wars. And then there was a Galvin committee, which was established to look at, could you consolidate the weapons activities into one laboratory? Why do we need two labs now that this war has been won? There's also the fear of big science, because the SSC had just been canceled. So DOE can't handle big projects. So we don't want to go down that rat hole again. We now had a Democratic administration with a very non-technical secretary, Hazel O'Leary, who ended up being a great supporter, but she was non-technical. And then something people don't remember or realize that both the Senate committees that authorize and appropriate the ICF program were chaired by Pete Domenici, also known as St. Pete in New Mexico. The last thing Domenici wanted was a big project in California. And of course, we had very strong NGO opposition because the NGOs like Tri-Valley Cares and NRDC saw this as an opportunity to get Livermore out of weapons. And so NIF became a vocal point for their opposition to the weapons program at Livermore and using NIF as the stepchild to go after. We also had against taxpayers against government waste. And I put Rick Spillman because that's a long story that some of you know, which I won't expand upon in private. I will. And there's Craig Olson. He was a scientist, a dancer at Sandia. And he was a strong advocate for Sandia. And one of the quotes, I remember him telling me, we don't need to worry about NES report. St. Pete will cover our needs. That's a quote from him. Next. All right, so you needed a technical mission. We talked about that. We talked about the technical program was very successful. AWNCA support. I remember telling Congress and such, there's 4 nuclear weapons labs in the world, design laboratories, Livermore, Los Alamos, CEA, and AWE, and 3 of them really like lasers. Los Alamos liked it, but 3 of them really like lasers. And so that was helpful. And CEA did a lot of contributions to the program. The mission expanded to be weapons physics, Z-pinch now, of course, was not done at that time, so we still had the monopoly that was coming, that was be lost later. And then political. This is something I want people to understand, is that we had strong political support. It's only been done once, I'm aware of. Every member of the California delegation, the 54 or so members of Congress, wrote a letter to Hazel saying, you got to do NIF. And on top of that, that was very important because in the first year of NIF funding, the House did not fund the construction project. There had to be a floor amendment to get NIF funded for construction, which was passed and was put in by a Democratic and Republican from California. We had, again, strong New York delegation support. And also, this is something which is a wonderful thing for people should always look at. We had an open letter from Hans Bethe, won the Nobel Prize for understanding SAR's work in the first head of the theory group at Los Alamos. Henry Kendall, Nobel Prize for showing that quarks exist in protons. And he was a founder of the Union of Concerned Scientists. And Herb York, first director of Livermore Arms Control Negotiator, they wrote a strong ed-op piece about NIF that was distributed in many, many newspapers that was used all the time. We also had good, strong, and then Harold Agnew. Harold became a big fan, and that's a long story about how Harold became a supporter of NIF. But he and I went to Domenici, and he convinced Domenici that Domenici should not oppose NIF. Strong industrial participation. Hoya glass moved the production into Hayward, California, for two reasons. First, we asked them to, and secondly, they wanted to not make glass for a nuclear weapons project in Japan. We had Kathy Brown, our mayor of Livermore, going back, supporting this, and of course, we had a standing NIF committee that was formed at Livermore that included people from the DoD, Science Committee on Weapons, and they all were supportive of NIF. Next view graph. And so the net result is Hazel came in late '94 and dedicated NIF. You see, there should be a plaque there. Livermore should put a plaque there. I don't know why they haven't, but they should. There's my daughter, of course. Anyone who knows me tries to exploit these moments. So my daughter and I drew a cartoon of a woman scientist shooting a laser into a target. And Chelsea gave that to Hazel. She loved it. And she sent Christmas presents to Chelsea for the rest of the time she was in the government. It was wonderful. There's Bruce and myself with a darker hair standing in the background. All right, next. We're getting close to being done. Next. So here's again, I'm highlighting Vic. There's a picture of Vic standing next to NIF. Now, I have seen this picture, but half of it is missing. Myself and my son, I use it to remind me how long this process has been going on. My son will be 26 in a month, this month. But that's what Vic came out. That was before anything was done with NIF. That's the future site of the National Ignition Facility. So all of you, when you go by and see NIF, that's what it looked like before there's anything there. And again, no one can ever give enough Vic Reese credit for saving the weapons program at Livermore, for establishing stewardship. You know, Vic is a true hero of this whole of the country, I believe. Next. And of course, here's the groundbreaking. If you look to the left, you'll see someone who looks like Chris Christie, but that's Bob McCrory in a little bit more expansive state. And there's Jeff and Dave and Scott Samuelson digging the first hole. Jeff does not get enough credit for the role he did in helping to design a NIF laser. Jeff is also one of the heroes of the program. I probably will draw him next, but he was digging a hole. Funny thing in there, after he dug the hole, Marilia Kelly from Tri-Valley Care came and tried to fill it up, and she put sunflower seeds in it. And my son came over and picked the sunflower seeds out of the pot, so it was fun. And there you see the NIF target chamber that came in later on. And you see, I just show that because it shows the ports for both symmetric and the traditional way of doing hull rooms. So NIF has always been viewed as something that would do all different approaches over its lifetime. Next. So NIF today, wonderful facility, doing enormously complicated and sophisticated work for the national security. And of course, beginning to see the onset of fusion alpha heating. It's a wonderful achievement by the laboratory and the community. And it's a great facility, no question. And there's Warren will be retiring soon, and so there's a picture of Warren doing some NIF planning as he's done for his career, and who's a major player in helping get NIF to be an experimental facility. Next. But it's not powered by fusion, right? Another thing that NIF did, and I was great to see it, is to be able to be the set of a science fiction movie, Star Trek. And so it's great to see that. And of course, I must have seen it 5 times, trying to find Bruno in there. Because remember, I didn't mention, but Bruno was Bruno was a laser scientist. Jack Campbell was a project manager. Neil Frank was a project engineer, and Bruno was a project scientist. I still remember interviewing Bruno at a little cafe with Howard Powell and Joe Kilkenny in Paris. And I'm glad that Bruno's been there with us ever since. Next. All right, now I'm going to end up with just a few other comments about large-scale facilities. These are obvious things, but you'd be surprised how infrequently they're followed. Next. So you need a successful program. Obviously, you need facilities, computations and modeling, diagnostics, and people. The key thing is people. Any one of those things are missing, you're going to have a program that doesn't succeed. And of course, don't forget targets. A boss would kill me if I didn't show that. There's him playing a soccer ball and holding both a direct drive target to remind him that he should worry about that too. Next. And so any strategy as we go forward, because we all hope we all know there will be something in the future. And these are common sense things, but you need a leadership that's inclusive. All the different elements have to be intellectual leaders and not just participants. Welcome, encourage criticism. Never think that you're right. One of the really great people at Livermore, Carl Hausman, made this one comment that I always remembered. There's a lot more smarter people outside the fence than in the fence. Never forget that. You need diagnostics which validate and prove modeling. We need 3D diagnostics to make understand what we need for ignition and gain. You need to have state-of-the-art simulations. Of course, all these things we do. You need a research program, of course, that is easily describable to a wide range of audiences. It's got to be inclusive. The failure of NIC has made this more difficult. We all have to recognize that. You got to have a point design, design that you evolves with learning, and you need a backup strategy and innovation. They have to be part of the strategy right at the beginning and utilize all facilities. Communicate with a broad community and stakeholders, and don't forget, we have to continue to develop laser technology. When the infrared catastrophe was found, the ICF program had no effort in nonlinear optics. Luckily, the rest of the optics community did that. We could borrow from them. We can't depend on them solving our problems in the future. We have to continue to develop better technologies, better approaches, and develop a supply chain that can do it. And of course, targets. We underfund targets to this day. Next. You got to have partnerships. There's Bob McCrory with let's just say, an unusual partner. That's a cartoon of President Obama and Bob. And I have a T-shirt of that. If anyone wants it, I'll be selling it for $5. Next. You have to avoid hype. And that's important. We all are enthusiastic and sell things, but we have to avoid hype. Here's a view graph that was presented in the Fusion Power Associates in 2009. And you can see the projections of NIF performance. People remember this, and I get it, and I'm sure Livermore, we all get it all the time. We have to be recognizing the challenges of getting this, and we have to keep our enthusiasm bounded properly and always say what we think the truth is. When I was doing this in Washington, you can imagine I would be asked by Congress to guarantee that NIF will get ignition. Now, I believed it, of course, but I said, I guarantee you it will get it, or if it doesn't, it will tell you what you need to get it, and it will be successful. But you have to view it in that context. And of course, I believed it at the time. I still believe we work hard, we'll be getting better fusion performance. But this is something which I get, a lot of people show me this whenever I talk about the future of ICF. Next. You got to keep costs under control. There's been successful projects keeping the cost under control, and then unsuccessful ones, but they still got done. I mean, I was the AD when NIF got started, so I own the cost issues that happened with NIF. But you still look at it, NIF was still done a lot cheaper than if we hadn't done all the other work. But NIF is very successful. DART has also had major cost overruns if you go back to the original thing, but it's a nice facility now. ITER had the same thing, it's underway. The SSE was canceled, Princeton Stellarator was, the Webb telescope is still, let's just say, not a guaranteed thing. There's a great book for people to read, and it's called Tunnel Vision. It's called The Rise and Fall of the SSC. It's a whole history of the LHC and SSC. The LHC also had enormous fiscal problems, but it got done. And there's a couple quotes in there, and here's one that's, our engineers, don't be offended by this, but this is a quote in there. Engineers must report to physicists, the users who are best able to make trade-offs when issues arise in cost. So it's, again, a lesson learned for the future when we try and get the next facility. Almost done. Next. Broaden the constituency. Look at all the HDP stuff we're doing. Just heard Livermore won the Dulles Award for work done on collisionless shocks. Great stuff. So we need to make this science is a wonderful tool, and it broadens people's interest in this field. There's very good stuff that Sandia's done on the Iron Pass, which is an ongoing program now with NIF and Sandia. Go on. Next. View the sponsor as a partner. The DOE they have a different responsibility than the performers, but they're partners. And so always have to engage them as true partners and be transparent. I used to talk to Dave Crandall every day when I was at the lab, and we got to continue always to have that. And sometimes it's I'll say a difficult relationship, but it always has to be done. There's Ernie Moniz. I have that T-shirt also for $5. And of course, there's our good friend Frank, who likes ICF2 for HEDP, and he's holding a target and a little model of Jupiter. Okay, next. And yes, as we look forward, I just want to remind people, and we always talk about what the future will be. Again, when I was doing a NIF, people would say, what about energy? And I said, look, I just flew across in a 747, and it's been less than 100 years since the Wright brothers. And that made them nod. And I thought, a good analogy. But then there's a great book on the Wright brothers that was done a few years ago. And it made me rethink. So I was right in connecting to the Wright brothers, but we're not looking back at the Wright brothers is the wrong thing. We are the Wright brothers. This is where we are right now. And could you imagine the Wright brothers? And they were geniuses and did wonderful things, not just flew for 20 seconds at Kitty Hawk. They were doing a lot of great things. Could you imagine them thinking what a 787 would look like? So we have to always continue to develop technology to take advantage of advances. And of course, who knows what the next facility will look like in lasers and pulse power, but I'll tell you, it's going to be different from what we have today if we continue to invest in it, and we need to do that. Next, almost done. It's going to require careers and dedication. I've been in this program and others for 40 years, and what I like to say, fusion is like it's a marathon relay race. It's going to be people are going to spend their careers and they won't be there to see the promised land like Moses, but like the famous prophet Moses. And one of the things that I was like, everyone should remember, when the medals are given out on the podium, those who started the race and those who finished it are on the podium. You need them all. This is a picture of John Sethian when he retired from NRL. And it's he's actually shrunk this, and he has model trains, and it's actually a billboard in his model train set. But it's a good picture. It's one of my favorite cartoons, a little bit more elaborate than typical. Next. And the last is, for all you listening, make this as a wonderful program and have fun in the process, and never not giving up having fun. There's myself with the young Magic Sam, who's a great blues guitarist. And I like music, and that's where I started. And of course, there's Bob McCrory playing golf with some of his favorite friends. So I think that's the end of my talk. It's gone a little bit longer, but I wanted to, there's a lot of stuff to talk about. And one of these next days, I'll give another talk on what I think the future could be. But thank you all, and thank everyone for listening in. Done.
Thank you very much, Mike. That was a very nice talk. If anybody'd like to stick around, you can ask questions in the chat field. So to access the chat field, you can move your mouse over the screen, and you should see a bunch of choices down at the bottom. One of them looks like a text bubble. We got a question from Mark Sherlock saying, are heavy ion drivers worth revisiting in the future?
The answer is the investment to get them going is enormous. There's a lot, so the answer is, on my list of priorities, it's something I would not put to the top. Are they worthwhile sometime in the future? Yes, but the problem with that, the investment to be able to do things, and we don't have a broad community working at. So there's a lot of interesting physics there, and Berkeley was starting to do some nice work on this before the program really got downsized. So the answer is yes, but it would not be at the top of my list.
Omar Hurricane asks, isn't your Wright brothers comment in contradiction to your point design comment?
No, but no, the point is, so the answer, Omar, it always changes. But you have to start, but it will always change. But it has to evolve. So you have to have an idea of what you need, and then it will evolve as you learn more, and this technology gives you more opportunities. But you have to have an idea of what, when you're doing something, you have to be able to have a concrete enough idea of what you could do at the time. And it's important, and the strategy also has to, a point design, there has to be innovation. I know that, we're doing that more and more, and that's a great thing to do. And you have to have always a plan B. But a point design is important because you have to initially be able to define the specifications of the facility, and that's driven by what it's supposed to do.
The question from Michael Cruz, if the US or other countries resumed nuclear testing, what would the implications be for the national ICF program? Good
point. So my own belief is that if we started testing, and I think that's highly unlikely for many, 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 many reasons. I mean, Las Vegas is a different place. That would really be a national emergency. But it would, the laboratory capabilities I think it will be an integral part. And historically, there has been laboratory facilities, back to the old radiographic stuff, back even in the Manhattan Project, will always play a role in the program, in the nuclear weapons program, because it's a way of testing people. It's a way of taking risks that you can't do. You're not going to do in a very expensive underground test. And obviously, there would be a lot of stress on the budgets and such, but laboratory facilities, I think, will continue to play a role in the national security, no matter, even if we went back to testing, because you can do more things here, you can diagnose better. Like, and one of the challenges of looking at failures in the weapons program, the underground testing, is when something failed, it was hard to figure out many times what happened. You didn't have failure diagnostics. Most of the stuff were based on emission measurements. And so when things fail, you would not know. And obviously, the world is three-dimensional, so having multi views in multiple directions is something not easily done underground. So my own view is, and I would hope the weapons program would endorse that. Kim Bedell and everyone else is doing that. That the laboratory facilities will continue to play a major role in stewardship, no matter what happens in terms of the future.
So Omar Hurricane asks, if NOVA was so successful, how come the projects with respect to the National Ignition Campaign didn't seem to be right? Do you mean NOVA was a public relations success rather than a technical one that informed the National Ignition Campaign?
Oh, no, well, no, it was a technical success also, but it was limited. It only had 30 kilojoules and 5 beams on a side. So it could not address issues that you could do with that a machine 100 times larger is able to do. So no, so NOVA did as best as it could, and it was successful. It's more than a public relations thing, Omar. It actually demonstrated a lot of the technology that you needed, at some of the diagnostics, and it learned did a lot of the physics that was necessary for NIF. Of course, when you scale by a factor of 50 to 100, you're going to be in regimes that you didn't do. Cryogenics was something that was not done for lots of reasons. It was not cost effective to do it. And then again, there was a time, to go after NIF when the testing stopped, and people were looking for what to do. And so NOVA was a technical. Remember, HEP started basically with NOVA. All the work on the science that we do, we call HEP, started with NOVA. We have filled to all the issues we're looking with engineering structures on capsules, and the whole rooms of these bigger plasmas were not addressable on NOVA given the scale size. So no, it wasn't a public relations. That's a complete false way of looking at it. But would I do NIF today based on what we've learned over the past years? No, NIF would be different. We would not be. We'd have a lot more wavelength flexibility we have on NIF. We'd have a lot more beam smoothing we have on NIF, because that would have affected the ability to do gas-filled whole rooms, I think, and which is a problem as we know now. No, NOVA was a success, and everyone would gear that. Everyone who viewed it at the time would view that. But you expect new things, and that's why it takes time to move forward. NIF is doing that now, and so I hope that over the next decade or so we will really iron out what we need to be able to get a real burning plasma laboratory.
There's a comment from Ed Hartooni essentially agreeing with you that the role of the laser played was another amazing story, and Livermore's and NRL's work on lasers from their invention to NOVA and NIF made astounding progress. Yes,
don't forget LLE in that too. Remember, Beams, SSD, and CPA came out of Rochester. So yes, the community, Rochester, Livermore, and NRL really advanced the laser technology. And it's actually the impact. Again, I just mentioned it, but 3 of the directed energy programs, which are being funded by the Department of Defense, all were either invented by people in the ICM program or utilize technology developed in that, which we don't make enough. We don't advertise enough with those stakeholders. Every time I tell the Pentagon that, they're surprised at where it came from.
Scott Wilkes asks, you saw all the transitions of Livermore lasers to the next generation. What do you see the next generation move for NIF?
All right, so obviously one of the things we have to do is continue to make NIF a more precise tool, and I know that's underway right now. I would like the program. We have a program at Rochester looking at making broader bandwidth lasers, UV lasers, and so developing that technology over the next 5 to 10 years, and maybe that could be implemented in NIF in the future. But and learning to continue. Livermore has done, I think, amazingly good work in learning to operate optics at high fluence levels. So to continue to push that is going to be something that, to be able to get more performance out of NIF at less cost will be an important part of that. But one of the things that I think we all need to do over the next, start is, we laser aficionados need to work together to really look at what would be a next architecture. Can you build a multi-megajoule laser for a cost that's affordable? And that's something which I think we're just in the beginnings of doing that. But we need to make we call them 4th generation lasers. First generation was CO2 and 1 micron. Second generation was UV. Third generation was putting some beam conditioning on these things with phase plates and other smoothing. And 4th generation, I think we'll try and make them as incoherent as we possibly can. The ideas that Bedros has done about the stud pulses, that's something we need to continue to develop, push the technology, which I hope is will come out of this Jason report that we need to be able to be prepared for the future, and it needs to look different from today.
There's a question from Bruce Cohen. How important was theory and simulation in making the case for going to shorter wavelength drivers, e.g. working with Bill Kruer or Max and others?
It was an essential component of that because this, required investments that the program not planned to do, and the work that Bill and his group did was essential. I remember when I first went to Livermore, I would spend a lot of time with Bill, and he'd teach me all the physics we needed to know. So absolutely essential. And one of the things I think is, I strongly believe right now in today's program, we've basically tried to find where plasma physics does, or coupling physics doesn't take place, or where it's minimal, and then operate in that parameter space. That's too restrictive. I think we need, my own strong belief, and we're doing it at Rochester, and I know other places too, is really reinvest and come back to understanding laser plasma instabilities and physics in a much more quantitative way than we've done in the past. And we have diagnostic tools now, I think, that allow us to do that. And modeling and simulation has grown too. So they were absolutely essential. Now, Bill's one of my heroes, and his team was too.
So Corby Ledgaudet asks, do you think that pulsed power technology and magnetic drives can compete with lasers?
It's a good question. I remember, I didn't talk much about pulsed power. I remember when Sandia went from the light ions to Z pinches. I remember this is back when the questions of heavy ions and light ions. I was a fan of the heavy ion program, when it was going on with Berkeley and the like. And I used to tell Sandia, the problem with light ions, it's like, let's throw a bowling ball into a hurricane, not a wiffle ball, because a bowling ball is going to go where you think it does. Light ions are not. So when they switched to Z, it's obviously been very successful. I mean, Sandia has done some really nice work. And you imagine the timing issue. So this goes back to maybe one of the other questions. When NIF was agreed to by the department, there was no alternative. No one else was doing high energy density physics and doing fusion research that was relevant. No one was doing that. Pulse Power was still doing the light ions. And so when NIF started, the project was underway. I remember, and we were a year or two into the project, getting a call from Jerry Jonas. I'll never forget it. He calls me up and says, well, we got a megajoule. I said, what do you mean? I got a megajoule of X-rays. What? You got a megajoule of X-rays? With the wire arrays. And, you can imagine, if this was 1995, when we had Pete Domenici running the committees, and we had a pulse power approach that was able to do relevant physics. What do you think? Do you think NIF would have happened? Think about that with Pete Domenici there. It would have been very, very difficult. So pulse power has made great strides, and it is a complementary approach to lasers. I mean, I like them both. And I think when you combine them like maglev and such, you see some innovative approaches. The challenge pulse power will have, and this is something that lasers benefit from because light can travel in a vacuum. You can't throw lightning bolts at targets. So as we go to higher performing targets and performances, the pulse power team is going to have to deal with the operational complexity that will come along with that. They can deal, I believe they will do it, but it's going to be very different operations than we do today. But no, I'm a big fan of pulse power. They've made enormous progress over the past 15, 20 years. And Dan Sonar just put out a paper from his review talk at APS, which I think is a great summary of the great progress they've made.
There's a question from John Moody. How do you view the role of pulsed power over the next decade? Will it increase in importance, be used in conjunction with lasers, et cetera? What do you think?
My belief at this stage, given where we are with both lasers and pulse power, it should be a balanced program, which means it needs to be supported. But if pulse power, lasers have not, let's just say there's still a lot of opportunities in lasers. The failure of NIF getting ignition to date so far is not a condemnation of lasers. It's actually shows us what we need to do. So my hope is that over the next decade, and the Jasons and others say that you have a very good situation. Look at, and you compare ourselves with what's happened in the magnetic fusion program. When you collapse to a certain one approach like tokamaks, you knock out all the other approaches with any reasonable scale. I'm sure many people would like to do stellar raters of scale, but they've been, at least in the U.S. and outside of what's going on in Japan and Europe, they don't get the attention that tokamaks do. And so we have the advantage where we have not only I think, attractive drivers, but we have a range of target concepts. So we got to make sure that this, this field of innovation, which relies on these things, it takes place. And because we have both drivers and innovative target concepts, the approach to both, that my hope is that we don't down select. A down select today or a re-emphasis that ignores the other thing would be a big mistake.
There's a question from Harry McLean. One takeaway is that teamwork is important, but also that individuals matter and can make a huge difference. Can you say something to the students, postdocs, and early career folks to remind them of this?
Absolutely. It takes as I said, it takes a team to do this. Interaction, cooperation, a work environment that is both challenging and friendly. Disagreements are something that should be done professionally, and you want that. You want people to have different opinions. And my view is that every idea is a good idea till proven wrong, not the other way around. Don't tell and I think that what that does, it makes people be encouraged to be innovation, makes them not afraid to ask a question or try a different idea. But individuals make a difference. Look at Vic Reese. We would not have this program today if it wasn't a person like Vic Reese. And so individuals, heroes are to be found, and and when you do, you take advantage of them. And so I hope one of these days we have a Vic Reese building at Livermore or a statue of him out front that everyone supports. So individuals are critical, and especially at critical times. It's very important that you have them. Think of what America would be like if you had Buchanan and Andrew Johnson in the 60s and not Abraham Lincoln. So it makes a difference, but you need community and collaborative activities. And there is no enemies. Someone who has a different idea is not an enemy, it's a collaborator, and you bring them into the fold. And when I was doing NIF, the dream I used to tell people that when NIF got ignition, the first author was from Los Alamos. That was one of the things I used to always go around as a true national facility. So absolutely collaboration, and laboratories need to work together, continuous as they are.
So Tammy Ma asks, what are your thoughts on some of the private industry forays into fusion and the promises they're making?
All right, well, so first, that they're making forays, I think that's great. It's interesting to see that people have begin to see that, we need carbon-free energy of scale, and people are going to put money into this, even when it's, as I'll say, as technically immature as fusion is as an energy standpoint. So I think it's a good thing, but what we have to be careful here is to temper it. Promising energy on the grid in 10 years or things like that, which we all have done in the past. I worry about that. And so I've been involved, Mark and I have been involved in talking to some of the private companies. And what our focus has been when we talk to the investors, be realistic. If you're expecting to make a lot of money in a short amount of time, then you're in the wrong business. But you can advance the field and make a contribution. And one of the things that ICF basically, I think, suffers from is these drivers can do so many different things. NIF doesn't spend all its time doing fusion research, Omega doesn't, Z doesn't. And so some of these private companies, if they're willing to establish laboratories that are dedicated to fusion research, energy research, that would be good. But it's my fear is that people will make promises that, again, it shows, the famous words of fusion's 20 years away and always will be. And you told me you'd have it 10 years before. So we got to be careful about that.
I would like to thank you very much again for the lovely seminar. And thank you to everyone out there for joining us and for spending this hour and a half with us.